Hey guys, I'm Bud of Math, and today I'll be showing you how to solve two variable systems of equations. So a system of equation is simply just multiple equations arranged in a system, right? And in today's video, I'll be showing you specifically with two variables, x and y. Now there can be three variable system equations, four variable system equations, but today we'll be focusing on two variables. So if you wanted to determine, say, a random point, like 3, 7, if this were a solution to the system of equations, what we would do is we would plug in our 3 for our x and our 7 as our y. So let's go into the first equation. If we plug in 3 here and we plug in 7 for the y, we end up with 10. So that means 3, 7 is a solution for the first equation. Now, what if we plug it in for the second equation? 9 times 3 is 27. And then 6 times 7 is 42, which equals 69. And 69 is not equal to 6. So this is not a solution to our second equation, meaning that 3, 7 is not a solution to our system. Now, what if we wanted to find a solution to a system of equations instead of deciding whether or not a pair of coordinates was a solution? So there are three different methods. The first one I'll be showing you is by graphing the functions or the linear equations, and the other two will be through substitution and elimination. So we want to find the solution to this system of equation. We have both of these equations in the slope-intercept form, which is y equals mx plus b. So let's start with our first equation. Y equals 1/2 x minus 3. Well, 1/2 x minus 3 is our y-intercept, so I'll mark this function in blue, and the other one I'll do in red. So we're going to start with our y-intercept at -3, so I'm going to put a circle here, a dot, a point, and then the slope is 1/2, meaning it'll go 2 to the right and then 1 up. So 2 to the right, so I'm at x equals 2, and then 1 up, -2, and then the function looks something like this. Right? And then in red, I'll do my other equation. Y equals -3x plus 1. Plus 1 is our y-intercept, so I'll put a point there. And then we're going to go to the left, to the right 2, and then down 3 because of the negative. So to the left 2 is x equals 2, and down 3 is y equals -2. And our line will look something like this. And to find the solution to this system of equation, what we're going to do is look at where the points intersect. So here is the point 2, -2. So our solution would be 2, -2. So the next method I'll be using to solve these two systems of equations will be the substitution method. And what that means is we're going to substitute one variable from one of the equations into that same variable in the other equation. Now, what do I mean by that? Here, I can see that x equals -1, which means that this value right here, which is also x, must be equal to -1 as well. So what I'm going to do is I'm going to substitute -1 into this x over here. So I'll end up with -2 times -1 plus 5y equals 7. And what's happened now is, if I simplify this to 2, I'll end up with an equation with just one variable. And what I can do is I can just solve for y. So I'll subtract 2 on both sides, and I'll divide by 5 on both sides, and I'll be left with y equals 1. So I know that y equals 1 is part of my solution for this system of equation. But what does x equal? Well, we found that x equals 1 from the start. It was given to us. So our solution for this system is negative 1, 1. What about this trickier mess? Here we don't have the luxury of having a variable equal to a numerical value from our system. But this is y equals negative 7x minus 5. And this is also y equals negative 6x minus 3. So both of these linear expressions are equal to y, meaning that these two linear expressions are equal to each other. So I'm going to write it exactly like that. Negative 7x minus 5 equals negative 6x minus 3. And what I can do from here is I can start solving for x because there's no more y. So I'll add 6x on both sides, leaving me with negative x minus 5 equals negative 3. I can add 5 on both sides, and then I'll have negative x equals 2, or x equals negative 2. And if I wanted to solve for y, well, I can just take either equation. In this case, I'll take the top one, but you could take the bottom one too. And when I'm going to plug in my found x value here into x. So instead of y equals negative 7x, I'm going to put y equals negative 7 times negative 2, and then minus 5, which means that y equals 14 minus 5, or y equals 9. And now we have our x and our y value for the solution, which means that we'll end up with negative 2, 9. Now, for the final method of solving these systems of equations, I'll show you how to use elimination. So, in elimination, you temporarily eliminate a variable from the two equations in order to form a new third equation with one variable. Now, what do I mean by that? We have these two equations, and notice we have negative 3y and negative 3y. If we were to subtract this equation from this one, so if we had 4x minus 3y equals 16, and we subtracted by this equation, minus 3y equals negative 19, well, we can rewrite this like 4x minus 3y equals 16, and then apply the negative to every single term. So plus x plus 3y, and then positive 19, so I'll do plus. Then we'll just do normal addition. 4x plus x is 5x. Negative 3y and positive 3y, they cancel. And 16 plus 19 is 35. Meaning that if we divide by 5, we get x equals 7. And in order to find our y value, we just plug in 7 back into one of the two equations. I'll use this bottom one. Negative 7 minus 3y equals negative 19. Negative 3y, if we move the 7 to the other side, is going to equal to negative 12, and then divide by negative 3, we'll get y equals 4. Meaning our final solution for this is 7, 4. So we just subtracted here. We could also add let's say this was a positive 3y, you could just add these two equations and then they would still cancel out, because when you're adding, you don't distribute a negative. So realistically, what I did was I multiplied the bottom equation by negative 1, right? So like negative 1, and then added them together. Now, in this case, we have two equations, and here again with the y, the 30y is realistically 10y times 3. And notice that it's plus 30y and negative 10y. So what you could also do is you could also multiply or divide one of the equations by a certain number in order to match them up. And what do I mean by that? Let's say I wanted to divide the first equation by 3. So I'll do 1/3 27x plus 30y equals 21. And then this will become, well, 27 divided by 3 is 9x 30 divided by 3 is 10y. And then 21 divided by 3 is 7. And then from here, because we divided on both sides of the equation, this equation is still equivalent to this equation. So these two equations are equivalent. And now we can use our second equation, the bottom one, and just add them normally. So I'm not going to put minus like I did on the other side, because what we'll see when I add them normally is we'll get 4x, the y's will cancel, and we'll end up with 12, meaning that x equals 3 because we divide by 4. And then we could just solve for y by plugging in x equals 3. I'll use the bottom one. So negative 5 times 3 minus 10y equals 5. That's negative 15 minus 10y. And then we can add 15 on both sides. So we'll end up with negative 10y equals 20, which means that y equals negative 2. And our solution for this system will be 3, negative 2. So the last thing I'll be showing you is how to determine the amount of solutions to a two-variable linear system. In our first case here, we have y equals negative 6x plus 3, and also y equals negative 6x plus 5. Notice that they have the same slope, but different y-intercepts. So on a graph, that would look like 3 and 5, and then the same slopes. Notice that they're parallel lines, meaning they'll never intersect. So the amount of solutions for this linear system is 0, or no solution. For this second system, we have two lines with differing slopes and differing y-intercepts. So what will happen is we'll have different y-intercepts. So it passes through negative 2, passes through 4. This one goes up like that. This one goes up like that. And eventually they'll intersect. So when they have different slopes, the y-intercepts don't really matter, but the slopes do. That means they'll have one solution. And here, when they have the same slope, but different y-intercepts, they'll have no solution. Now for our last example, we have 2y equals 4x minus 2 and y equals 2x minus 1. What I'm going to do is I'm going to divide the first equation by 2 completely so that we have it in terms of y. So 2y equals 4x minus 2, divided by 2, we end up with y equals 2x minus 1. And notice this is the same equation as the other one, as like the second one. So when you end up with two of the same equations, two equivalent expressions like we have here, we write IMS for infinitely multiple solutions. And what this means is that basically on the graph, they are the same line. They're exactly the same line. They'll pass through every single point. And that is it for systems of equations with two variables.